Welcome to The Explainer. Today we're diving into a massive cosmic detective story. We are going to look into one of the absolute most baffling mysteries in astrophysics. Namely, how exactly does the universe accelerate particles to these mind-bending, ultra-relativistic speeds? I mean, here on Earth, we have to build these massive, highly controlled, multi-billion-dollar machines just to get a tiny taste of this kind of physics. But out there in the cosmos, nature is doing it effortlessly all day, every day. And today, we're going to uncover her secret. Just think about this number for a second, 10 to the 20th power. We regularly observe cosmic rays smashing into our atmosphere with staggering energies of up to 10 to the 20th electron volts. To reach even a tiny fraction of that power in a laboratory, we have to go through immense trouble, building massive, magnetically confined machines like cyclotrons or tokamaks. It's honestly kind of funny when you think about it. When we try to build earthly machines to store high-temperature plasmas, the configurations are usually grossly unstable. It requires a frankly ridiculous amount of calculated human effort just to keep them from instantly falling apart. But these cosmic accelerators, they seem to do it without breaking a sweat. Nature generates these extreme energies completely naturally, without any of the artificial boundaries we rely on. So, what exactly is the engine driving this? Well, before we can officially name our culprit, we need an investigative checklist. Any viable astrophysical theory that tries to explain cosmic particle acceleration absolutely must follow these three rules. First, it has to naturally form a power law energy spectrum. Second, it has to explain how particles are pushed all the way up to that crazy 10 to the 20th electron volt limit. And third, the chemical makeup of these accelerated particles has to actually match the general abundance of elements we see out in the cosmos. Section 1. Solar flares and early ideas. So, where did scientists look first? Our own cosmic backyard, naturally. In solar flares, we observe this really fascinating process called electron runaway. Basically, in the neutral sheets of a solar flare, magnetic field lines reconnect and generate intense electric fields. When an electron in this plasma hits a certain critical velocity, inside what physicists call a Dreiser field, the drag from collisions just drops off. The electron essentially runs away, accelerating with zero impediment. But there's a fatal flaw here. As these particles beam forward, they create return currents and streaming instabilities that actively neutralize the electric field. So the energy is strictly capped. Solar flares are cool, for sure, but they definitely aren't our primary cosmic culprit. Section 2. Fermi's original mechanism. To find the real answer, we actually have to rewind all the way back to 1949. The brilliant Enrico Fermi originally envisioned the interstellar medium as being filled with these moving magnetic clouds. He proposed a stochastic or entirely random process where charged particles literally bounce off these moving magnetic mirrors in space. It's essentially a giant cosmic game of pinball. It sounds great, but there is a massive mathematical flaw in Fermi's 1949 idea. See, when a particle hits one of these clouds head-on, it gains energy. Awesome. But when it catches up to a cloud moving away from it, a following collision, it actually loses energy. Because the clouds are just moving randomly, a particle is going to experience both types of collisions. Sure, there's a slightly higher chance of a head-on collision, but because of all that back and forth, the average energy gain is only second order. It's proportional to the velocity of the cloud squared, which is a fancy way of saying it is agonizingly slow. So Fermi's early theory essentially hit a brick wall for three big reasons. First, as we said, that second-order acceleration is just way too slow, since cloud velocities are tiny compared to the speed of light. Second is the injection problem. Particles start out with low energies, meaning they lose all their juice to basic ionization long before the random clouds could ever speed them up. And third, there was absolutely nothing in this theory to explain why we see a universal power loss spectrum across the cosmos. It was a beautiful idea, totally ruined by reality. So how could particles possibly overcome these massive hurdles? Section 3. Diffusive shock acceleration. Fast forward to the late 1970s, and multiple scientists independently stumbled upon an absolute game-changer. They called it diffusive shock acceleration, or first-order Fermi acceleration. They realized, hey, you don't need random magnetic clouds. You need a massive supersonic shockwave, like the kind blasted out by a supernova. When a particle interacts with a continuous shockwave, the geometry changes completely. Suddenly, every single crossing becomes a head-on collision. Just picture a highly supersonic supernova shock advancing relentlessly through the interstellar gas. Because our cosmic ray particles are moving near the speed of light, the shock itself actually seems slow to them. When these particles are scattered by turbulence in the gas, their velocities become totally randomized on both sides of the shock front, the upstream side and the downstream side. You can really think of it as a relentless cosmic ping-pong match. A particle crosses the shock from the quiet upstream gas into the violently moving downstream gas. Because the downstream gas is moving relative to the upstream, it acts like a giant wall moving toward the particle. Whack! It gains energy. Then it scatters and diffuses back across the shock into the upstream. But wait, relative to the downstream, the upstream gas is also moving toward it. Whack! Another head-on collision. The particle just bounces back and forth, multiplying its energy on every single pass without fail. And here is the real aha moments. When physicists finally ran the math on this constant back and forth bouncing, they didn't just find that particles got fast. They discovered that the exact rate at which particles escaped the shockwave perfectly produced a power law spectrum of e⁻². It mathematically aligns with exactly what we observe out there in the universe. Boom! The mystery of the spectrum was solved.
Section 4, Magnetic Fields and Supernovae.
But of course, in astrophysics, solving one mystery usually just uncovers another. It turns out there might be a strict limit to a standard supernova's horsepower. When calculations were done in the 1980s by Lagrange and Cesarski, they found a serious problem. A normal supernova blast wave only lasts a peak strength for about 1,000 years. If you calculate the energy using the standard strength of an interstellar magnetic field compressed by a shock, it maxes out at about 10 to the 14th electron volts. Now that's a massive number, sure, but it is way, way short of the 10 to the 20th electron volts we are looking for. Something had to be massively amplifying the magnetic fields to hold the particles in the ping-pong match longer. We know the math isn't lying to us because we can literally see it happening. When we look at breathtaking Hubble Space Telescope images of Tycho's supernova remnant, we see an incredibly narrow, sharp filament right at the edge. That right there is non-thermal X-ray emission. It's physical, visual proof of ultra-relativistic electrons losing their energy right at the shock front. The fact that this filament is so narrow proves that the magnetic field in that specific spot must be incredibly, unusually strong. So, how exactly does the field get so incredibly strong? Well, it turns out the particles themselves are doing it. As these high-energy cosmic rays stream ahead of the shock, their own electrical currents physically push on ambient magnetic loops in the plasma. This creates these violent instabilities that tangle and amplify the magnetic field by a factor of 100 to 1,000 times. This brilliant little feedback loop perfectly solves the limit problem, allowing these souped-up supernova shocks to accelerate protons up to 10 to the 17th electron volts and heavier nuclei like iron even higher. Section 5. The highest energy particles. Okay, so we've pushed supernova shockwaves to their absolute limits, but what about those monster particles at 10 to the 20th electron volts? Well, if we look at the famous Hillis diagram, which plots the physical size of an object against its magnetic field strength, we see a solid diagonal line. That line is the absolute mathematical threshold required to reach 10 to the 20th eV. And as you can see, typical supernova remnants fall just a bit short. Which leaves us with our final mystery. At the extreme top end of the energy spectrum, our local supernovas fail us. The culprits have to be something else entirely. If these ultra-high energy particles are protons, they might be getting fired from the blindingly powerful relativistic jets of massive active galactic nuclei millions of light years away. But if they are heavy iron nuclei, they might be generated by unique, hyper-energetic, and currently unknown events much closer to home. And that brings us right to the very edge of human knowledge. We've cracked the code of the power law spectrum. We've proven that shockwaves act as nature's effortless, incredibly efficient particle accelerators. But I want to leave you with this final thought to ponder. If even the mighty exploding supernovae can't power the absolute most energetic particles we see striking our atmosphere, what monstrous engines are lurking out there in the dark that can? Keep wondering, and thanks for joining me on this explainer.